Next, we're going to look at the pressure gauge. And what we're doing here is, let's say we have a tube and we fill the tube with mercury. So this portion right here is mercury. And then on one side we pour water. And of course, since water is less dense than mercury, it will float on top of the water. And it'll push then, of course, the mercury on one side of the tube a little bit higher. And then the question is, what would be the difference in height between the top of the water on one side and the top of the mercury on the other side if the column of water is 15 centimeters high? So how do you do a problem like that? Well, the best way to do is find a place in the tube somewhere where you can say that the pressure is the same. And if I take the very top of the mercury on the left side, which is being pushed down by the water, and I go straight across the other side of the tube to this location right there, I can say that the pressure at this location must equal to the pressure at that location, because there's nothing but mercury underneath all the way to one side and the other side. So I know that the pressure at those points are equal, which means that the pressure over here is caused by this height of mercury, and the pressure over here is caused by this height of the water. So if I call this pressure 1 at this location, and I call this pressure 2 at this location, I can say that pressure 1 equals pressure 2. And of course, we know that pressure inside a fluid is caused by the density of the fluid and the depth of the fluid. So we can say that pressure 1 can be written as rho 1 G H1, which means the density of fluid on this side and the height of the fluid on this side equals the rho 2 G H2, which means the density of the liquid above this point on the right side and the height on the right side. So this right here could be considered H2, and this then would be considered H1. And then density 1 represents the density of water, and density 2 represents the density of mercury. All right, so I see a G on both sides, which means I can get rid of the G on both sides, cancel those out. And since I already know what H1 is, I'm going to figure out what H2 is equal to. And turning the equation around, I can say that H2 times rho 2 is equal to H1 times rho 1. And then dividing both sides by rho 2, I can say that H2, which is the height of the mercury above that point, is equal to H1 times the ratio of rho 1 divided by rho 2, right? H1 is 15 centimeters, and I can leave it in centimeters because I'm just going to get the answer in centimeters. So this is 15 centimeters times the ratio of the density 1, which is the density of water, which can be written as 1 gram per cubic centimeter, divided by the density of mercury, which can be written as 13.6 grams per cubic centimeter. And then, if I then take 15 divided by 13.6, I get 1.10. So this is equal to 1.10 centimeters. Which means the height of mercury, that gives me the same pressure as the 15 centimeters of water, is 1.1 centimeters. That's of course why they use mercury in barometers, because you don't need as much of it to be able to measure the pressure. And then of course, ultimately, since we want to know the difference in the height, in this case delta H would simply be equal to H2 minus H1, which is 15 centimeters minus 1.1 centimeter. So therefore this is 13.9 centimeters of difference between the two columns, water on the left and mercury on the right. So the whole trick is, this is not a hard problem if you just realize, find the place in the tube where the pressure is exactly equal on both sides with the same height for both of those points. And that's how you do that problem.